So up to this point, everything's been pretty abstract. We have lots of chemical potentials, lots of partial derivatives. But now let's think about conceptually what types of systems we can consider. Our starting point is going to be the idea of an ideal solution. And so we need some way, what we really, most of this is constants, right? If a constant temperature and pressure in terms of understanding chemical potentials. All right, this is a fixed value. R and T, we're considering a specific temperature and pressure. And so, we'll vary those, but at a given temperature and pressure, this is constant. So really what we need to understand is this term here. How do we find this PJ value? PJ star is going to be some specific value as well. So it's really, we need an expression for what is the vapor pressure of our solution, of one component of our solution, and how does that change? How does PJ change with respect to composition? And or we could think of this as concentration. We'll usually write this in terms of mole fractions, though. Specifically, like, given a specific value of xj between 0 and 1, can we predict the value of pj? And then that would tell us about the chemical potential. So our starting point here is an ideal solution where we have a pretty simple expression for this. But let me first talk about conceptually what an ideal solution is, and then why we get the particular expression we do. Now, there are, I will say up front, unlike ideal gases, which describe most gases at sort of room temperature and atmospheric pressure, ideal solutions are not the norm. Most things behave non-ideally in terms of talking about liquid-liquid solutions. But what an ideal solution would be, it'd be two things mixed together that are basically very similar to each other, and therefore don't really exert any different forces than you would expect. So an ideal solution is one where the two components of the solution behave almost identically. And what I mean by that is specifically thinking about their intermolecular forces. So sort of our two assumptions that are required for an ideal solution are first that the molecules are roughly the same size and shape. All right, so you want things that take up roughly the same amount of space, and so that what we want is that you want a random distribution of your two different components. All right, and the second assumption is that the intermolecular forces are all about the same. And specifically of component 1 interacting with component 2 is about the same as 1 interacting with 1 or 2 interacting with 2. These are all similar. Okay, so I want you to pause the video and think for a minute. What two, often we're thinking about organic solvents, what two types of molecules could you mix together that would satisfy this sort of condition? So hopefully you actually paused the video, thought about this, maybe wrote down some ideas, and I'll give you a couple of examples. One really good example of an ideal solution is something like a mixture of benzene with a mixed with liquid toluene, where all that changes is that we have a methyl group on here. Right, so these two things are going to behave very similarly. There's not big chemical differences. One's not polar, one's not nonpolar. They're both very nonpolar. Another example is something else where you have just one methyl group difference between the two, something like hexane, right? And heptane, where we just add a methyl group on the end, right? This would be something else that would have close to an ideal solution behavior. Now, these are pretty specific examples, right? And so, like I said, most solutions are not ideal, but this provides a good starting point. And so, if the solution is ideal, let's think about what's happening in terms of the vapor pressure, right? That's what we're interested in. And vapor pressure really is a surface phenomenon. Okay, so if we have our surface of our solution, if things are randomly distributed, we roughly have an even distribution, provided the mole fraction's equal, of 1s and 2s at the top, at the surface of the solution, right? Things at the surface it's going to be random. And so the fraction of molecules of 1 or 2 that you have at the surface is just going to be the same as you'd have throughout the rest of the solution, right? So it's just the mole fraction. So what we can say is that the vapor pressure above this solution, right? So this is Pj up here. You know, there's P1 and P2. We're going to have two different P's here. Vapor pressures we need to worry about. This is just going to depend on the mole fraction of J times whatever, sort of scaled by whatever the pure substance vapor pressure is. Because if something is more volatile, if its vapor pressure under normal, at this temperature and pressure is higher than the other component, you would expect it to be higher in the vapor phase as well, even if you have a mixture of them. And this equation is known as Raoult's law, and this gives us a way to find Pj star, right, as a function of, gives us a way to find Pj as a function of the composition. And so this lets us look at some properties of that. And so we will look at that in the next video.